A team of astronomers pointed a telescope at one of the oldest, most densely packed collections of stars in our entire galaxy, hoping to answer a fairly specific, well-defined question. How do the individual stars inside this ancient cluster actually move relative to each other? That was the whole plan. Measure motion, track velocities, standard, careful astrophysics. Instead, when the team sorted every single star in that cluster by brightness and color, something showed up that nobody was looking for at all. A gap. A thin, precise, unmistakable void where a specific population of stars should have been sitting and simply wasn't. Andrea Bellini, one of the researchers behind the discovery, put it about as plainly as a scientist ever does. They weren't looking for the gap, but they found it anyway. This is the real story of what the European Space Agency's Euclid Telescope just revealed inside an ancient star cluster. Why the missing stars point to something happening deep inside stars that scientists have never been able to observe this clearly before, and why this specific gap, once you understand what's actually causing it, becomes a genuinely powerful new tool for measuring the universe itself. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this particular gap mattered enough to make headlines, you first need to understand exactly what kind of object NGC 6397 actually is, and why astronomers consider globular clusters like it to be some of the most valuable natural laboratories anywhere in the galaxy for studying how stars actually work. Ein NGC 6397 sits roughly 8,000 light-years from Earth in the southern constellation Aura, making it one of the closest globular clusters to our own solar system. And it's genuinely ancient, estimated to be around 13.4 billion years old, meaning it formed when the universe itself was still remarkably young. It's also a member of a specific, somewhat rare category of globular cluster that astronomers describe as having undergone core collapse, a process where the cluster's central region has contracted over billions of years into an extraordinarily dense concentration of stars, packed together far more tightly than the cluster's outer regions. What makes clusters like this so scientifically valuable comes down to something Massimo Grigio, the principal author of the research team's published study, described directly. Globular clusters function as ideal laboratories for studying stellar evolution and stellar populations, specifically because every star inside a given cluster sits at essentially the same distance from Earth and formed at approximately the same time. In a typical patch of sky, stars you're observing can be wildly different ages and wildly different distances from us, all tangled together, making it genuinely difficult to isolate how a single specific stellar property changes over time. Inside a globular cluster, that entire problem disappears. Every star shares roughly the same birth date and roughly the same distance, meaning any differences you observe between individual stars come down almost entirely to differences in their original mass, giving astronomers an unusually clean, controlled environment for testing their theories. The research team, based at the Space Telescope Science Institute in Baltimore, combined observations from two of the most capable space telescopes currently in operation, the European Space Agency's Euclid Telescope and NASA's Hubble Space Telescope, specifically to study the internal motion of stars within NGC 6397. Actually pulling off this kind of precision measurement inside a cluster this densely packed is genuinely difficult because individual stars sit so close together in the sky that separating one star's light from its immediate neighbors requires extraordinarily careful analysis. The team leaned on more than 2 decades of specialized analysis techniques and software originally developed specifically for Hubble's own observations, tools refined over 20 years of studying exactly this kind of crowded stellar field, and combined that expertise with Euclid's considerably wider field of view, which allowed the team to study a much larger portion of the cluster at once than earlier, narrower observations had ever managed. It was while sorting through this combined dataset, grouping the cluster's stars by their brightness and their color, essentially building what astronomers call a color magnitude diagram, a standard foundational tool used throughout stellar astrophysics, that the missing stars became visible, right in the portion of that diagram corresponding to a very specific range of low-mass red dwarf stars, stars with roughly 34 to 36% of our own sun's mass. There was a thin, clearly defined gap, a stretch of brightness where the population of stars simply dropped off, far below what the surrounding data would have predicted. Here's where it's important to be precise and honest about exactly how surprising this specific finding actually was, because the underlying physical phenomenon itself wasn't entirely unknown before this study. This particular kind of brightness gap among red dwarf stars had actually been identified once before, back in 2018, using data from the European Space Agency's Gaia mission. An earlier survey that had spotted a similar gap while studying red dwarf stars in our own immediate stellar neighborhood close to the Sun. That earlier discovery earned the feature a name, the Jiao Gap, after the lead researcher on that original 2018 paper. So the phenomenon itself, and the general physical explanation behind it, wasn't a complete unknown walking into this new study. What genuinely was new, and what makes this specific Euclid observation significant, is that this is the first time this particular gap has ever been detected inside a globular cluster at all. Every previous detection had come from studying relatively young, nearby stars in our own galactic neighborhood. Finding the same feature inside a genuinely ancient 13.4 billion year old extremely dense stellar population was a discovery nobody working on this particular study had specifically set out to make. The physical explanation behind the gap itself comes down to a genuinely subtle transition happening deep inside the interior structure of certain red dwarf stars. Stars transport the heat generated by their internal nuclear fusion outward toward their surface using two fundamentally different physical mechanisms, depending on their specific mass and internal conditions. Some stars rely primarily on radiation, heat simply moving outward as electromagnetic energy passing through the star's interior layers. Others rely primarily on convection, a physical process much closer to how boiling water moves in a pot, where entire columns of hot material physically rise toward the surface, cool down, and sink back toward the core over and over. For stars sitting right around this specific narrow mass range, roughly a third of our own sun's mass, something interesting happens as they gradually evolve. Well, their internal structure transitions, shifting from having a partially convective interior, where some parts of the star transport heat through convection and other parts still rely primarily on radiation, to becoming what astronomers describe as fully convective, where convection takes over as the dominant heat transport mechanism throughout essentially the star's entire interior. That structural shift, though genuinely subtle on the surface, ends up altering the star's overall luminosity in a specific, measurable way, and the result is exactly the kind of narrow gap in the brightness distribution that both the original 2018 Gaia study and now this new Euclid observation of NGC 6397 have independently detected. What makes this specific new detection genuinely useful, beyond simply confirming that the same physical process happens inside ancient globular cluster stars too, is a practical application the research team has already identified. Russell Ryan, another of the study's primary researchers, explained the significance directly, because researchers can now determine the precise brightness at which this gap occurs, and because they know exactly which stellar masses correspond to that specific transition, that information can be used as a genuinely precise tool for estimating the cluster's actual distance from Earth. Distance measurement remains one of the fundamental, persistently challenging problems throughout astronomy, and having an additional, physically well-understood reference point like this gives astronomers a valuable new method for calibrating and cross-checking distance estimates to globular clusters, on a category of object that plays an important role in broader efforts to understand the age and structure of our entire galaxy. It's also worth appreciating what this discovery reveals about the sheer analytical difficulty involved in confidently identifying a feature this subtle in the first place. NGC 6397's status as a core collapsed cluster means its central stars are packed together with genuinely extreme density, making the basic task of cleanly separating one star's light from its immediate neighbors a serious technical challenge on its own, before you even get to the more difficult work of precisely measuring each individual star's brightness and color with enough accuracy to detect a gap this narrow and this subtle. The fact that the missing star pattern only became clearly visible once the team combined Hubble's decades of refined crowded field analysis techniques with Euclid's substantially wider observational view speaks directly to how genuinely demanding this specific measurement actually was. The research team has also been clear and appropriately measured about where this specific finding leaves things moving forward, rather than treating this single detection as a fully closed case. Their published paper notes that further investigation, using both Euclid's ongoing observations and eventually NASA's upcoming Roman Space Telescope, characterize this same feature across other globular clusters as well, building toward a broader, more complete picture of exactly how consistently this internal stellar transition behaves across different clusters, different ages, and different environments throughout the galaxy. So here's where this genuinely leaves things, honestly, based entirely on the team's own peer-reviewed publication in the journal Astronomy and Astrophysics. A research team set out to study something specific and well-defined, the internal motion of stars inside an ancient globular cluster, and stumbled entirely by accident onto physical evidence of a genuinely subtle structural transition happening deep inside certain stars, a transition that had only ever been observed before among much younger stars in our own galactic backyard. Finding that same signature preserved inside one of the oldest Like most densely packed stellar populations in the galaxy, wasn't something anyone on the research team had planned to look for, and it turned into a genuinely useful new tool for measuring distances across the universe in the process. That is not manufactured drama built around an exaggerated headline. That is the honest, on-the-record account of exactly how this specific discovery actually happened, published by scientists at the Space Telescope Science Institute, using two of humanity's most capable space telescopes working together. If this kind of story is what you come here for, one grounded in exactly what astronomers actually found and openly explained, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly a lot more waiting to be found by accident in the data we already have. Drop a comment telling me whether you think this same gap will show up in other ancient star clusters once astronomers go looking for it. And share this with someone who still thinks every major discovery in astronomy comes from a deliberate, planned search rather than a genuine accident.